So before we get to the derivative patterns, we do need to talk about some notation first here. And I thought it'd be good to start with the familiar old linear function, x and y, rise over run. And you may have seen this when you wrote out the slope in your algebra class, is that this can also be shorthand with some notation by using the delta symbol. Now, delta always means, in math, it always means final minus initial. And in this case, it's written as 2 minus 1. And that's what delta means. We have delta y over delta x, and it means exactly this. And this delta notation represents this picture here. And recall with calculus, the derivative, the limit, that we're now going to take x2 and x and y2. Well, as we take x2 and get it closer and closer to x1, this will cause y2 to get closer to y1. And this can happen forever. That's the limit. This is where infinity comes in, that we can get forever closer to x1. And in algebra, these are numbers. In other words, this might equal 0.1 over 2. But as we take this into calculus, this notation, it's actually going to go, these deltas are going to turn to these little d's. And it's common to mistake these d's for derivative. And there's nothing necessarily wrong with that, but it comes from the delta. And in calculus, where this represented some number, this no longer represents some number. This represents this idea now of getting forever and ever closer. In other words, dy, remember the limit is all the numbers except the one we're interested in. So this is all those numbers except the one we're interested in. As is common to say, this is the transition from algebra to calculus, that these finite values here end up going into these infinitesimals. And this is our new notation. And this notation does mean the derivative. And y here is just the name of the function. We can name the function whatever we want. Of course, it's common to call it f. But, we could also change the function name as well as the input name. And then that carries over to the notation. Let's focus on the common one here, using f. And that this symbol means the derivative function. Just like f of prime means this is a symbol for the derivative function. And what we're going to do is we're sort of going to peel this f off. Just peel it off the notation there. And then what's left, this, is then what's called the derivative operator. Now, operator notation is not something we're going to talk about. However, the notation is used in our book and is commonly used at this point in calculus, although operators themselves are more advanced topics. But this can get confusing when students see this symbol versus this symbol. And this means the function, whatever your derivative function is. That's what this symbol means. This, however, you should think of as more of an instruction. It's a command. It's telling you, take the derivative of whatever comes next. So think of this as an instruction. It's saying, take the derivative of whatever function comes next. And we're going to use this notation. The book does as well as MyMathLab. And so this is our two pieces of new notation. The symbol for the derivative and the symbol that's telling you to take a derivative. So let's check this out, how this works, this operator. And here's just a standard writing a function. I'm going to say, f of x equals x squared. And with algebra, you would do things to both sides. Maybe you would add 2 to both sides or take the square root of both sides. Well, what we're going to do in calculus is we're going to take the derivative of both sides. And how do we indicate that? We indicate that with the derivative operator. So now we're saying we're going to take the derivative of both sides. And when we do that, the f, the function notation, will just slot in here to the operator. So just slot it in there. And on the right side, then, it's telling us, take this derivative. So the left side, notice the left side transformed to the symbol for the derivative. And on the right side, we have to take the derivative. And the derivative of x squared is 2x. And so then we have our derivative answer. And so just take a moment and look how the notation, how the operator notation transforms into the symbol for the derivative. And on the right side, you carry out the command and you do the derivative. And again, this is exactly the same notation as f prime. They both have their uses, as why they're still widely used today. So going forward now with these derivative patterns, now that we have some notation, is remember the quadratic function. You had a, b, and c, and you learned in algebra that you can solve this for x, and you got the quadratic solution, something you've probably all remembered. And you know that no matter what you choose for a, b, and c, you will always get an answer from this formula. X is solved. This is always the solution for x. X always has this pattern. And I want to call that a pattern just so I can call these things some name. So I'm going to call this the pattern. Because it turns out that the derivatives that we've been doing also have a pattern. In other words, if you're given a derivative, there is a pattern to the solution. And let's take an easy one. A constant function. So this is a function that can be any number. It can be 2, could be 100, could be -8. C can be any number. And because it's constant, means x plus h is also c. So no matter what we plug into the function, we're always going to get the same output. That's what it means to be constant. And we're going to plug this into the definition of the derivative. So we'll get a c here and a c here. And c minus c is 0. And this is important right here. Notice that no matter what number you choose, it will subtract out right here, and thus it no longer matters what number you choose, because it'll subtract out. And so c minus c is 0. And now remember, as h goes to 0, h never becomes 0. So this is never 0 divided by 0. Remember, plugging in the number is the simple thing to do. But don't forget, you never become this number. In other words, this is always 0 divided by some positive number. And 0 divided by some positive number is 0. And the limit of a constant is always that constant. So what did we just do here? We just figured out the pattern for this derivative. No matter what function that's a constant, any constant function you want to choose, the derivative will always be this pattern. The derivative of a constant is always 0. And this is what I'm going to call the derivative pattern, just to give it a name so you know what I'm referring to. And with our operator notation, this is how we would write it. So this is the command. It's telling us to take the derivative. The derivative of a constant is always 0. So take the function 5. Put it in our, we'll take the derivative of both sides with the operator notation. The f slots up into the notation, and the derivative of a constant is always 0. And notice if I choose a different number, the derivative doesn't change. Because that's what it means to be the derivative pattern. It's always this. Even if I choose some larger number, the derivative pattern for a constant function is always 0. Now, unfortunately, this is the only one that we can prove at this point. We don't have the tools to go through these other patterns. So I'm just going to state them. There's 3 more here. All 3 of these patterns can be proven in a similar manner to how we just went through. So here's pattern 1. The derivative of a constant is always 0. The next in line, power functions. So power function is like x squared. Or x to the minus 10. A power function is x raised to any number n. And the derivative of a power function always has this form, this pattern. Exponential functions. So that's like 2 raised to the x, or e raised to the x. Those are exponential functions. And the derivative of an exponential always has this pattern. And notice that the derivative of an exponential always contains itself. Just something easy to remember there. And then the last one, logarithm functions. So for exponential, we have base. Base is the b, and that's the same b that's here in the log function, base b. So let's check out some examples of these. These are the 4. For the rest of the semester, we're going to be using burn them into your brain. Burn these 4 patterns into your brain. And check the handout that's also with this lecture in the modules of Canvas. So I want to stress that constant power exponential logarithm, that specifically means the functions right here in the parentheses. Because going forward, you want to be able to identify which function you have. You want to look at your problem and you want to say, okay, I have a power function. And once you identify what function you have, you'll then use its derivative pattern. Or maybe you're looking at a problem and you're like, okay, I see I have a log function. Well, if it's a log function, then here's the derivative pattern. So going forward, for the rest of the semester, it's going to be crucial that you can identify when you have one of these 4 functions. All of the functions going forward will be one of these. And once you identify the function you're using, or the function you see, or for the problem, then here's the derivative pattern. So let's check out some examples for the constant function. So any number, derivative of 5 is 0. The derivative of minus 1,341 is 0. The derivative of 0 is 0. The derivative of pi is 0. The derivative of a number is 0. The constant function always has a derivative of 0. All right, so question 1. What is the derivative? Well, the derivative of a constant is always 0. But the power function, good old x squared. So what do? You want to recognize that for a power function, the variable is in the base. So you can see our variable here is in the base. And so then we identify the exponent with n. And then we look at the derivative pattern. We see n drops down to be a coefficient. So there it is. And then we do 2 minus 1, which is 1. X to the 10th. We identify n as 10. And then we look at the derivative pattern. So we have 10x to the 10 minus 1 to get us our 9. X to the minus 100. Identify n as minus 100. So minus 100 will become our coefficient. And then for the exponent, we have minus 100 minus 1, which is how we then get minus 101. And how about x to the pi? Pi is just a number, about 3.14. So we identify pi as n. And so pi becomes our coefficient. And then for the exponent, we have n minus 1, which then is pi minus 1. Power functions. How about exponentials? Now notice with exponentials, just going back real quick, for a power function, the variable is in the base, but for an exponential function, the variable is in the exponent. So that's how you know how to identify which is which. Is your x in the base, or is your x in the exponent? So here's a power, here's an exponent. Power function, exponential function. So question 2, what is the derivative? Identify 6 as n. So the 6 becomes the coefficient. Subtract 1 from the exponent. 6x to the 5th. So 2 to the x. We identify b as 2. And then so b is 2. What if it's 17? Just do the same thing. So b is now 17, and we'll just plug b in. The derivative pattern. The derivative, this is the derivative. The derivative of an exponential function will always have this pattern. And again, I could just make these numbers larger. Doesn't change anything. It's still the same pattern. Now, a special case is when the base is e. And so here's the pattern. Nothing's changed. However, log e is 1. And so we get this case that the derivative of e is itself. So besides 0, the derivative of 0 is itself, and the derivative of e to the x is itself. So it's a special case. The book will use these examples a lot. The derivative of e is itself. So question 3, what is the derivative? Well, identify 5 as b, and so we'll have the natural log of 5 times 5 raised to the x. And finally, for the log pattern, remember b is the base, just like for the exponential function. So we'll identify 2 as the base. Using the derivative pattern, we plug 2 in. Same with 23. Just plugging 23 in. Well, first we identify 23 as b, and then we know what b is for our solution, our pattern. Now remember, with logarithms, if there's no base written, then it's understood to be base 10. So if there's no base written, it's understood to be base 10. And this is called the common logarithm. The common logarithm is base 10. And base e is the natural logarithm. And a natural logarithm gets its own notation. It's just ln. So ln is the same thing as log base e. The same thing, just different notation. And just going through the pattern here, the derivative pattern, and log e is 1. And so we get this other special case that the derivative of the natural logarithm is just 1 over x. So it doesn't have this extra factor here because log e is 1. So 2 more things to say here. Those are the 4 derivative patterns that you're going to want to know for the rest of the semester. So no messing around there. Burn those in your brain. And we're going to do plenty more practice of all of those. Question 4. What is the derivative? This is the common logarithm, which means base 10. So we identify b as base 10. And so the derivative is 1 over log 10 times x. That the derivative distributes. So it distributes just like you know how distribution works. There's nothing tricky here. Now, the math statement for this might look a little scary. So distribution means it goes across plus and minus. So here's our derivative operator. If we're going to take the derivative of 2 functions being added or subtracted, then the derivative distributes. And so that's what I have written on the right side then. The derivative operator distributes. And this is real handy because if we have something complicated here with a plus and minus sign, then we can break it down into 2 simpler parts. So the fact that the derivative distributes is enormously useful. So let's check out an example. So we have this function here. Now the first thing you want to be able to do is identify what function is that there. It's a power. And over here we have a log. This is the first thing you want to do. Identify which functions you have so you know which derivative patterns to choose. So we're going to take the derivative of both sides. Now the derivative distributes. So we can take the operator and distribute it to both functions. And now that we've done that, we can use the derivative patterns to then do these derivatives. Question 5. What is the derivative? Well, the derivative distributes, so we can do them each term by term. So we first recognize we have a power function, and so that derivative pattern gives us 3x squared. We then recognize the next function is the exponential pattern, and the derivative of e is itself. And then we recognize the next function, which is a constant function, and the derivative of constant is always 0. And there's our answer. Constants we can pull out of the derivative. And what do I mean by this is, let's say we have some function multiplied by some number. So this could be like 3 times x squared. So we have some function multiplied by some number. When that's the case, this number we can pull outside of the derivative. We can pull it out of the derivative. So it's common to say that this is inside the derivative, and then everything else is outside the derivative. And so the c is inside, and then it's outside. So constants we can pull out of the derivative. So let's say we have this function here. So it's the same function we had last time. In the last example, we had x cubed and log x. But this time I'm just going to multiply them by some numbers. Take the derivative of both sides. The derivative distributes. And so we get down to this point here, which is the same point as the last time. However, now we have these constants. And now these constants we can pull outside of the derivative. And now we have the derivative patterns. And now that we've reduced this to the derivative patterns, we just use them. So the derivative of x cubed is 3x squared, and the derivative of log x is 1 over x. And then finally, we just clean up our answer. Question 6. What is the derivative? So we can distribute, so we can do these term by term. And we know the constants will pull out of the derivative. So we're just looking at the derivative of log x, which is 1 over x, the derivative of x to the fourth, which is 4x cubed, and the derivative of e to the x, which is itself. And now we look at the constants. So we have a 7, a plus 5, and a minus 2. And so we would get a 7 over x plus 20, x cubed minus 2e to the x. So in summary, 4 derivative patterns. And if you're worried about memorizing these, we're going to use these so much on test 2 and test 3 that you're just going to memorize them. You're going to use them so much. And remember, for exponential and log, when you have base e, there's a special case. When you have base e, the derivative of e is itself, and the derivative of natural log is 1 over x. So in general, there's 4 derivative patterns here. These are just special cases. However, you might want to say altogether there's 6, however you want to think about it. And the derivative distributes. Hugely important. And another useful property is that we can pull constants outside the derivative. Try to burn all of this into your brain and check out the practice video to see me working through these problems. Get some practice. The best way you're going to burn this into your brain is by practicing. I'll talk to you in the next lecture.